This video is part of Electrify Everything, a very short course. In this episode, we ask, how do we use energy every day? So the topic of energy in school is a very important one, but it can also be pretty confusing. So let's keep it simple and start with how we think of energy intuitively. Food like bread and fuels like coal contain energy. We use the energy stored in food and fuels to make things happen, such as transportation, heating, lighting, cooking, and in the case of food, living. We can imagine energy as a kind of stuff that's contained within food and fuels. Let's use a sponge full of water as an analogy. A wet sponge is a water carrier, similar to how food and fuels are energy carriers. The water in a sponge is invisible, just like the energy in food and fuels is invisible. But while we can squeeze water out of a sponge and it can exist on its own, energy needs a carrier. It can't exist by itself. We measure energy in joules, similar to how in the metric system we measure length in meters and mass in grams. And it's named after this guy, James Joule, who developed the concept of energy in 1850. In the metric system, the prefix kilo means times 1,000. So 1 kilojoule is 1,000 joules, just like 1 kilometer is 1,000 meters, and 1 kilogram is 1,000 grams. Different foods have different amounts of energy stored in them. These numbers show how many kilojoules of energy are stored in 1 kilogram of each food source. For reference, a 1 liter bottle of water is about 1 kilogram and has 0 energy stored in it, while 9 full sticks of butter is around 1 kilogram as well, but it has 32,000 kilojoules stored in it. And an average adult needs 8,700 kilojoules each day, which is the same amount of energy as a 2,000 calorie diet. We just use calories instead of kilojoules in the United States. So if an average adult eats 800 grams of bread, which is about 80% of a big loaf, they'd have all the energy they needed for that day. Similarly, different fuels also store different amounts of energy in each kilogram. I bought a small piece of coal that fits in my hand, which has a mass around 50 grams. From this chart, I can calculate that 50 grams of coal, which is 0.05 kilograms, contains 1,500 kilojoules of energy. So let's imagine that we burn this piece of coal in a power plant. And you can learn more about power plants in another video, Where Does Electricity Come From? And we calculated earlier that our lump of coal will release 1,500 kilojoules of energy, and we know from that other video that electricity generation is around 35% efficient, which is close to a third, and that means that 2/3 of the energy is wasted and 1/3 is transferred by electricity. But actually, that's the total amount of energy that the coal could release, and we're not specifying how long it would take to burn all that coal to run these devices, since we don't know how much energy these devices need. If they only use a relatively small amount of energy, you could think of the energy released by the coal taking longer to get used up. And this is represented here by the thinner arrows and a much lower energy transfer rate, which we call the power. We measure power in watts, and there's a device called kilowatt that lets you measure the power through a regular wall outlet. The unit of power is named after this guy, James Watt, whose heat engine improvements helped kickstart the Industrial Revolution. And you can learn more about heat engines in this video, how wasteful is our energy use today. And 1 watt is defined as 1 joule flowing in 1 second. And again, that's the energy transfer rate, which is separate from the amount of energy stored in a fuel such as coal, which is named after that other guy, Joule. Okay, so the power is the energy transfer rate, and we can use the kilowatt to measure it. So first, I'm going to plug in an old school incandescent light bulb to the kilowatt. When I plug it in, the kilowatt measures around 40.2 watts, which is a little more than the 40 watts printed on the package. Okay, so now I'm going to plug in a modern LED bulb, and measures around 3.6 watts. And that's a little bit less than the 4 watts it says on the package. But that means that the LED bulb uses 10 times less energy than the incandescent bulb for the same amount of light. In this experiment, I have the incandescent bulb on the left and the LED bulb on the right. They get turned on together, and on top it's a regular camera recording them. On the bottom it's a special thermal camera, and you can see the incandescent bulb on the left heats up as it turns from the cool blue that it started at to the hot orange, while the LED bulb stays a cool blue the whole time. Both bulbs produce about the same amount of light, but the incandescent bulb produces a lot of waste heat, while the LED bulb produces very little. If we add some estimates of the efficiencies of the bulbs, we can put numbers on the energy flows based on what we measured with the kilowatt. For the incandescent bulb, around 4 watts is going to light and 36 watts is going to heat, while for the LED bulb it's around 2.5 watts going to light and 1.1 watts going to heat. So if we now trace the 40 watts of energy going into the incandescent bulb back to a coal-fired power plant, and the coal-fired power plant wastes 2/3 of the energy coming from the coal, then the 4 watts of light is only a tiny fraction of the 120 watts that's coming from the coal, and the rest is wasted in the power plant and in heating the bulb. Instead, to power the LED, if we trace the 3.6 watts back to the power plant, it's a much larger fraction of the 10 watts that's coming from the coal. And we can do even better if we power the LED bulb with energy from a spinning wind turbine, since there's very little energy lost from the turbine to the bulb. And if we power it using solar, there aren't even any moving parts. And this is the future we want to get to. Efficient electric appliances powered by renewable energy sources with very little waste heat produced. Okay, in summary, energy is stored in food and fuels, is measured in joules. It's the energy transfer rate is called the power, which we measure in watts. It flows a lot for high power and a little for low power. And energy lets us compare how well we're using fuel, as we saw in the incandescent versus LED bulb. So if you've got any questions, email us, schools@rewiringamerica.org.